Welcome back, students. This is the session 20 from the playlist of electric charges and field. The topic for this session is the calculation of electric field intensity due to the non-uniform charge distribution. So I have taken here one question which pertains to this topic, and the question here is: a solid insulating sphere of radius capital R has a non-uniform charge density given by rho is equal to AR square, where A is a constant and this small r is the distance measured from the center of the sphere. So the magnitude of the electric field outside the sphere is, there are four options here and we have to find the correct one. So here the charge density rho is equal to AR square. Now this is the volume charge density. There are three types of charge densities which we have studied in this chapter. One is the lambda. This is the linear charge density. The second one was the sigma, which was the surface charge density, and rho. Rho is the volume charge density. So here the volume charge density is equal to AR square, where A is a constant and R is the distance measured from the center of the sphere. So here I have drawn here one small figure. So this is a solid insulating sphere, and it is having the center at this point, that is O. Now here what I have done is that I have taken one portion of this sphere which is having a radius of R and a thickness of dr. So the first thing which we have to do using this form, this equation, is that we have to find the total charge which is on this solid insulating sphere. So now rho is equal to A R square. Now if I consider this portion of this insulating sphere having a radius R and thickness of dr, then rho, which is equal to AR square, will be equal to the total I'm just considering right now this portion of this insulating sphere having a radius R and a thickness of dr. So for this portion of the sphere, the volume charge density, which is equal to AR square, can be written as dq upon dv. Okay? And here from this expression I will get this dq will be equal to AR square dv. Okay, now this equation can now be written as 4 pi r square into dr. Now what is 4 pi r square? This is the surface area of this portion of the sphere, and if I multiply it by the thickness of this sphere, that is dr, then I will be getting the volume of it. So dq is equal to AR square multiplied by 4 pi r square dot dr. So from this equation I am getting that dq is equal to 4 pi A R4 dr. So if I integrate this equation from 0 to R, where R is, this capital R is the radius of this insulating sphere, I will be able to find the total charge which is present on this insulating sphere. So this is equal to 4 pi A R4 dr. So from this equation, the total charge on this insulating sphere will be equal to, now this 4 pi A are constant because A is also a constant, then so this can be taken out, and finally I will be getting this equation as 4 pi A is taken outside and this is equal to, simply we have to integrate this R4 and from 0 to capital R. So Q will be equal to 4 pi A. Now Q will be equal to 4 pi A. The integration of this R4 will be equal to R5 upon 5, and we have to integrate it within the limits of 0 and r. So the total charge which is associated or we can the total charge which is present on this insulating sphere will be equal to 4 pi a r 5 r to the power 5 divided by 5. Now we have to find the magnitude of the electrical field outside the sphere. Okay, so the magnitude of the electrical field outside the sphere, for this I will be using the Gauss law. Now as per the Gauss law, the flux passing through a closed surface is equal to Es cos theta, and this is equal to Q upon epsilon naught, where Q is the total charge enclosed by that Gaussian surface. So in this case, if there is a point, say here, there is a point P here. So if I construct a Gaussian surface here, so the total charge enclosed by the Gaussian surface will be equal to this value. Okay? So the electrical field at the point P will be equal to, say, E, and the S is what? It is the surface area of that Gaussian surface. So in this case, if I say that this point P is located at a distance r, then I can write this surface area as 4 pi r square, and cos theta, this theta is the angle made or is the angle between the direction of the electric field and the normal to the surface. So here the value of theta will be equal to 0, so cos 0 will be equal to 1. So finally I am getting this equation as E dot 4 pi r square, which is equal to this Q enclosed. That is the charge which is enclosed by this Gaussian surface, and this Q enclosed is equal to this value, that is 4 pi a r5 upon 5. So 4 pi a into r5 divided by 5 epsilon naught. So this is the equation which I have got finally, and by solving this equation, we will be able to get the value of the E as a capital R to the power 5 divided by 5 epsilon naught r square. So the intensity of the electric field at a point outside this insulating sphere, solid insulating sphere, will be equal to a r to the power 5 divided by 5 epsilon naught into r square. So here the correct option is A. Okay, so in this question, there were two important things. First thing is that you have to find the total charge which is present on this solid insulating sphere, and then you have to simply use the Gauss law in order to find the intensity of the electric field at a point outside the solid insulating sphere. So thank you very much for joining this session. In the next session, I will be coming up with the same topic, that is the calculation of the electric field intensity due to the non-uniform charge distribution. But in the next session, the question will be different from what we have studied in this session. So till then, have a nice day. Bye.